Hello and welcome back to another video. In this problem, we're asked to explain using theorems 4, 5, 7, and 9 why the function is continuous at every number in its domain and to state the domain. So we have n of r is equal to inverse tangent of 1 plus e to the negative r squared. And so what we are going to do is to split this up into different functions. So we're going to have a of r is equal to the inverse tangent of r, b of r is equal to 1, c of r is equal to e to the r, and d of r is equal to negative r squared. And these functions are, respectively, a inverse trig function, a polynomial, an exponential, and a polynomial. And we know from Theorem 7 that these functions individually are continuous over their domains. And if we write this n of r, this is equal to a of, because it's inverse tangent of, 1 is b of r, plus e, which is c, of e to the r, that exponent is d of r. So this is a of b of r plus c of d of r. And so we can simplify this as the composition of functions and the addition of functions. So Theorem 4 states that if b of r and c of d of r are continuous at some point, their addition b of r plus c of d of r is as well. And the composition of functions is discussed in Theorem 9, which states that if d of r and c of d of r exist at a point, then c of d of r is continuous at that point as well. And if tangent, which is a, is continuous at a point, and what's inside b of c of d of r, b of r plus c of d of r is as well, then the whole thing is as well. Therefore, due to this addition and compositions, we can say that the whole thing together, n of r, is continuous at every number in its domain. What is that domain? Well, we have certain domain restrictions that are caused by individual parts of the function, right? And so the easiest thing to note is that the two polynomials have no domain restrictions, right? And then we can say, okay, exponentials also don't have domain restrictions, and the inverse trig functions sometimes have domain restrictions, but inverse tangent does not. Therefore, n of r is continuous at every number in its domain, and that domain is all real numbers.